last time we talked about some properties that you can measure about stars, like their mass, luminosity, and temperature. And today we're going to see how we can combine all of that data to compare and contrast different stars, and how we can use that data to talk about populations of stars. And the way that we're going to combine all of that data together is in what's called the Hertzsprung-Russel Diagram. So that's what's shown here. And if there's one graph that you can take away from this class that you have the ability to read, it would be this figure here. If you can read this graph, then you can extract a lot of information about stars. To review, we could measure the luminosity of a star by first measuring the brightness of a star by just pointing your telescope at it and using your eye or your detector to measure its brightness. And then if you can measure the distance to that star, then you can calculate the luminosity. One of the ways we can calculate distance, especially to the nearest stars, are by using parallax. So the amount of angular distance that it appears the star moves due to Earth's orbit around the sun, you measure that angle and you use this formula to calculate a distance in parsecs. And then if you have a star in a binary system, you can use Kepler's laws as modified by Newton to calculate the masses of the two stars in the system, if you can measure the period and the distance between the two stars. So those were the properties that we could measure, and now we're going to put all of those properties on this Hertzsprung-Russel diagram. So first let's review. So if the star Vega was moved so that it's now twice as close to the Earth as it currently is, how would its brightness change? So we're moving Vega closer to the Earth, and we want to know what its brightness is going to be. Yeah, so brightness goes as the distance squared, or inverse of distance squared. So if it's twice as close, 2 squared is 4, and then since we're moving it closer to the Earth, it has to get brighter. If we were moving it farther from the Earth, it would get dimmer and it would be half as bright, or a quarter as bright. So brightness, take whatever number, in this case 2, square it, and then if it's closer to Earth, it gets brighter. If it's farther from Earth, it gets dimmer. Okay, so we're going to talk now about the Hertzsprung-Russel diagram, or HR diagram. And we'll pick out some interesting populations of objects on the HR diagram, and then we'll talk about what the main sequence of stars is. So this is a full HR diagram, and what you're plotting on the y-axis is the luminosity, and then on the x-axis is decreasing temperature. So the highest temperatures are on the left side of the x-axis, and the lower temperatures are on the right side of the x-axis. And then luminosity just increases as you go up the y-axis. So we're going to take all of those luminosities and temperatures that we figured out from the stars we're studying, and we're going to plot those on this graph. So you can see lots of different stars on this kind of diagonal line, and then there's different populations spread out in different places on the HR diagram. And so our job this class is going to be to learn how to extract as much information from this diagram as possible. If we just zoom in on that diagonal strip of stars, those are called main sequence stars. And most stars that you're going to see in the sky are going to be on the main sequence. And so generally, as the temperature of your star increases on the main sequence, its luminosity is going to increase. If you're up and to the right of the main sequence, then you have a large radius of your star, or you have a low temperature, but you have a lot of luminosity. And so anything that's to the above and to the right of the HR diagram are called giants and supergiants. So there's stars that are, as it turns out, they have a much larger radius than the stars on the main sequence. And when we talk about the evolution of stars, we'll see why that is. So that'll be in a couple lectures. And then there is a population of objects that are below and to the left of the main sequence, and those are white dwarfs. So they have very high temperatures but very low luminosities. And it turns out that they have very small radii. So those are white dwarfs, and again, those are going to be a consequence of the evolution of a star throughout its lifetime. And we'll come back to that also in a couple lectures. You can get more complicated with your classification of stars. So on the temperature axis, you can see labeled the spectral types O, B, A, F, G, K, and M. And those were originally classified by the different amounts of ionization of different elements in their spectral data. So for example, the sun is a G star, and then the 2 is basically the spectral types cover a very large range of temperatures, and so we subdivide the G letter into 10 different segments, and so the sun is a G2. Then we add a Roman numeral after that to say what kind of star it is. So if it's a 5 Roman numeral, then it's a main sequence star. But as soon as you evolve off of the main sequence, then you'll become these different kinds of giants or supergiants. And so we can classify the star by their spectral type, and then also by where they live on the HR diagram. So the X and Y axes are temperature and luminosity, but there's actually a lot more data that you can extract from these diagrams. So like I said, the temperature maps to the spectral type, so that information is on there. You'll see the stars are color-coded, and these are by how they would appear to your eye. So there's red stars down at the bottom of the main sequence, then they become more orange and yellow, and then up through blue. And also I talked about the stars that are up and to the right of the main sequence have a larger radius. And so that is also something that you can gather from the HR diagram. So this is a very dense, this graph is very dense. There's a lot of information embedded into it. So it might be hard to see from where you are, but there's these diagonal lines that are not quite parallel to the main sequence, and those are radius values. So as you go up the HR diagram, you're increasing the radius of your star. So let's practice how we would read this diagram as a class. So we have these different options for where a star might live. And so of these choices, which star is the hottest? And you can just shout it out. Okay, so we have a B. Any other selections? A, yeah, so the x-axis is your temperature, so you want to be furthest to the left on the x-axis. So the A choice is even farther left than the B choice is. But it would be A is the hottest, then B, then D, then C. Okay, then which star is the most luminous, or which star has the highest luminosity? Yeah, so luminosity is the y-axis, so you want the one that's highest up on the graph, and so that would be C. So C is the most luminous, and then it would be B, then D, then A. Okay, which of these options is on the main sequence? Yeah, D. So the main sequence is this diagonal strip of stars, and D is the only one that's on the diagonal. And then which star has the largest radius? Yeah, so remember the radii kind of go not quite parallel to the main sequence, and so as you go up the graph, up and to the right, you're increasing your radius. So C would have the largest radius, and then it would be B, then D, then A. So that's generally what we do with the HR diagram. Is very quickly you can compare lots of different stars and get a lot of information out of them. So this strip of stars that goes diagonally we call the main sequence. What is so special about this region of the HR diagram? Why are there so many stars here? So it turns out that main sequence stars are ones that are converting hydrogen into helium via the nuclear reactions that we talked about earlier. So if a star is doing nuclear fusion, turning hydrogen into helium, it's on the main sequence, and so all of these stars on this diagonal strip that's how they're powering themselves. And on the main sequence, the most luminous stars are bluer and hotter, and then the red stars are much cooler and less luminous. We'll talk about what happens when your star is not doing hydrogen into helium reactions later. Also on the main sequence, so we've talked about radius, but now we're going to talk about mass. So as you go up the main sequence, you're increasing the mass of your star. So the red ones are cooler, less luminous, and they have much lower masses. And the ones that are up and to the left have much higher masses, much more luminosity, and much higher temperatures. And you can see the sun is kind of in the middle here. It's not the most massive, but it's not very small mass either. And so when we talk about star formation next time, all of the characteristics of the star are basically going to be determined by the mass that it has when it starts doing fusion reactions. So the mass will determine temperature, luminosity, and as we'll see in a second, how long that star is going to live. So if we remember back to what a star is, we have this big ball of gas and plasma that has a lot of mass, and so there's a lot of gravitational attraction that's trying to compress it all together. And the thing that's stopping the gravitational collapse is the energy of the nuclear reactions happening in the core. And so for all of the main sequence stars, those nuclear reactions are converting hydrogen into helium. When you have a bigger mass for your star, you're going to have even greater gravitational attraction that's trying to collapse it, and so you have a lot more pressure pushing down on your core, and you're going to increase the rate of your fusion reactions. And so that's why the higher mass stars on the main sequence are hotter and more luminous, is because of this battle and balance between the inward pressure, or the inward force of gravity, and the outward pressure from the fusion reactions. So let's review our properties of stars that we saw last class. So the luminosity of a star, the lowest luminosity stars are going to go from 10 to the minus 4 times the luminosity of the sun. So take the luminosity of the sun and divide it by 10,000. Or on the high end, you can be 10 to the 6 times the luminosity of the sun, or 1,000,000 times more luminous than the sun. The temperature is going from 3,000 to 50,000 Kelvin, and the mass is going from 0.08 solar masses to 100 solar masses. And we just said that the sun is really going to determine all of these properties. So those 3,000 Kelvin stars are going to have a mass of 0.08 times the mass of the sun, and the 50,000 Kelvin and up stars are going to have over 100 solar masses. And same for luminosity. So your initial mass that your star starts out with is going to determine the temperature that it reaches when it does its nuclear reactions, and the amount of energy per time that it's putting out into space, all determined by the mass of the star. And that mass is going to be tied to the lifetime of the star. So the sun's expected lifetime is about 10 billion years. So we're maybe halfway or a little past halfway through that time frame. So this is not something we need to imminently worry about, but eventually our star is going to stop doing its normal nuclear reactions, and we'll see how that's going to change things in the upcoming lectures. So for a star that's 10 times the mass of the sun, it has 10 times as much fuel, but its luminosity is much greater, so it uses that fuel 10 to the 4 times faster. So even though it has more fuel to burn, it's burning it at a much greater rate. And so that star is only going to live 10 million years compared to the sun's 10 billion years. And then on the opposite end of the spectrum, so a star that has 10% the mass of the sun, it has less fuel, but it uses it much less quickly. So a lower mass star can live for hundreds of billions of years. So there's a large range for how long a star can live given the mass that it starts out with. Okay, so on the main sequence, we have this kind of a range of stars in terms of their masses and lifetimes. And you can see the higher mass stars are bluer. They have very short lifetimes and very large radii. And then on the lower mass side of things, they live for a lot longer. They have a smaller radius and they're redder with lower luminosity. But all of these stars are converting hydrogen into helium in their cores. Okay, so if we have red, orange, yellow, blue, and white stars on the HR diagram, why are there no green stars? Green is a color in between yellow and blue. So I'll let you guys think about this for a few minutes. Why are there no green stars on the HR diagram? Yeah, so it turns out this is kind of a trick question. So there are green stars, and humans are just very bad at perceiving stars as green. So this does come back to how humans perceive color. So in our eyes, we have cones that are sensitive to different colors of light, but those cones are not evenly distributed amongst the colors, and there's a lot of overlap. So we have cones that are good at detecting blue light, and so you can see the curve of ranges that would activate a blue cone. Then you have the green sensitive cones that overlaps with the blue and the red, and then you have these red cones that are sensitive to red, but also all these other colors. So stars are black bodies, so they're going to emit light at all of the different wavelength ranges. So, for example, a green star is going to emit light, it'll peak in the green, but it will emit light in red and blue also. So, basically what's happening is any star that's going to peak in the green is going to also be hitting our red sensitive cones. It'll activate the green and the red sensitive cones. And so there's red and yellow and orange in between these, and so there's no way to only activate the green photoreceptors. So any star that would peak in green is going to show up somewhere in between green and red. But for stars that are very red, it's going to activate the red sensor more than any of the other ones, and then stars that are mostly blue are going to activate the blue sensors photoreceptors more than any other cone in your eye. And so it turns out the sun would be a green star if we were better at seeing green. So if you know anything about biology, we have plants that do photosynthesis. And what color are the plants that do photosynthesis? Green, because that's where they can get most of the light energy from the sun. So the sun is a green star It's just that the way humans evolved to see color, we're not good at isolating a green star from a red star. So kind of a trick question, but it's interesting interplay in biology and astronomy. Okay, so that's a brief summary of the main sequence, but what are all those other things on the HR diagram? What are the giants and supergiants and white dwarfs? So on the main sequence, you're turning hydrogen into helium in your core. So once those reactions stop, then your star is going to change. So you're going to break that equilibrium between the inward force of gravity and the outward pressure of the nuclear reactions. There's a couple different ways that can happen, and we'll talk about that in a few lectures when we talk about stellar evolution. But when they're no longer doing hydrogen into helium in their core, the star is going to puff out its radius and become a giant or a supergiant, depending on what mass it started with. So this is kind of the immediately after leaving the main sequence, they'll become a giant or supergiant. Much later on in the process, when all of your fusion reactions have stopped, then you could become a white dwarf. So a white dwarf is basically going to be the exposed core of a star after it loses all of its outer layers. So to give you a sense of scale, so here's the Earth and the Sun for comparison. A white dwarf is about the size of a planet, and so this is the exposed core of a star, basically. So it lost all of the gas around it, and this was the core of the star left over. So this little dot outside of this zoom is the sun, and now you're comparing the sun to a giant star and then a supergiant star. So Betelgeuse is a supergiant star, and you can't even fit it on the same slide as the sun and still be able to see the small speck that the sun is. So stars can get very, very, very big once they are evolving off of the main sequence. And so here's a nice visualization of some of the different objects that we've studied so far this semester. So we started with the moon, and now we're seeing the different terrestrial planets in the solar system. And then you can see the jump to how big the gas giants are. And then an even bigger jump when you're comparing those planets to stars. And then very quickly, the sun will start to be dwarfed by these giant and supergiant stars. So you can't even see the sun or any of the planets when you compare it to some of those very high mass stars at the end. Let's now individually, we'll do these as a quiz question. So just show you a bigger picture first, and then we'll go to the quiz in a second. So for the first quiz question, you're asked which of these stars is most like the sun. Yeah, so the sun is a main sequence star, so we're going to pick one of the stars on the main sequence. So B and C are supergiants, and A would be a white dwarf, so D is the only one that's a main sequence star. Then we'll do another quiz question, so which of these will have changed the least in 10 billion years? And then we'll go to the quiz question. Okay, so this one is a bit tricky. So remember, as you go up the main sequence, your lifetime is getting shorter. So B and C have already evolved off the main sequence, so their lifetime is very short. They're in the stages of dying, basically, B and C. A is already dead, and so it turns out this one is not going to evolve very much. So A is actually the correct answer. D, we said, is a star like our sun, and the sun is, we said its lifetime is about 10 billion years. So in 10 billion years, the sun will be evolving off of the main sequence and become a giant star. So the correct answer is that the white dwarf, the remnant of a core of a dead star, basically is going to change the least in 10 billion years. The Hertzsprung-Russel diagram is just a very convenient way to contain a lot of information in one graph. So the axes are just plotting luminosity versus temperature, but from that you can get a lot of other information like the mass, the lifetime, the radius, the spectral type, all contained into one diagram. And then the giants, supergiants, and white dwarfs are going to be what happens to a star after it evolves off of the main sequence, meaning what happens to it after it stops fusing hydrogen into helium in its core. So one of the interesting things that we can do with the HR diagram is use it to study star clusters, and more specifically the ages of stars in a star cluster. So there's two different types of star clusters. There are open clusters where you have maybe a few thousand stars that are they're not very close to each other, but they are still interacting with each other gravitationally very loosely. Then on the other extreme of things, you have globular clusters. So these, you have up to 1 million or more stars in a very dense region of space, and they're all interacting with each other very strongly gravitationally. So the sun is not in a globular cluster because we do not have a lot of stars like this very close to us. So how can we use the HR diagram to study the ages of these star clusters? So the technique that we're going to use is called the main sequence turnoff. So if we look at a cluster of stars and make an HR diagram for just that cluster of stars, we'll see that most things are just going to be on the main sequence of the HR diagram, But if the cluster is old enough, we'll start to see some of those stars starting to evolve off of the main sequence. And so kind of the last place that you see something on the main sequence and then where you start to see things evolving off of the main sequence is called the main sequence turnoff. So that means that if there were stars that formed in this cluster up here, they've already evolved off the main sequence and met their fate. So they've died in some explosion or some other event. So the fact that we're only able to see these kind of stars will tell us that this cluster has to be at least old enough for these stars to have gone through their whole life cycles and then started to evolve off the main sequence. So for this cluster, this is the Pleiades, and there's no stars that have a life expectancy less than 100 million years, so there's no stars up here. So that's telling you that the Pleiades star cluster has to be at least 100 million years old. It can't be older than that, or the stars down here will have started to evolve off of the main sequence. And so the stars in these clusters, they might not have formed all at exactly the same time, but they will have all formed at roughly the same time. And so if they're all starting their life at the same time, then the higher mass stars are going to die first, and then the lower mass stars are going to die at the very end. So basically, by doing a population study of the stars in a given cluster, you can use this main sequence turnoff technique to figure out how old that cluster has to be. And so if you plot a bunch of different clusters together, so here we have Persei in the diamond, the purple diamonds, and so you can actually see a lot of high luminosity, high mass stars here that haven't yet evolved off of the main sequence, and so this cluster must be fairly new. Then the Pleiades we talked about, there's not really high mass stars left, so they've all died, so this cluster must be a little bit older. Then for the Hyades cluster, again, there's not any stars up where the Pleiades has their turnoff. The turnoff is much further down the main sequence, so that cluster must be older. All of the blue X's that were higher up in the HR diagram have already died. And then for these tan squares, you can see they're all the way, not all the way down the main sequence, but pretty far down the main sequence. And so any stars that were bigger have already died in the NGC 188 cluster, and now the stars that are evolving off the main sequence are the less luminous, less massive stars, which live longer, and so this cluster is 7 billion years old. So the HR diagram is useful for just being able to compare and contrast different stars, but using this main sequence turnoff technique, it's also very useful for studying the ages of star clusters that we find in our galaxy and in other galaxies. So when we do this modeling for globular clusters that we find in space, we see that those globular clusters are at least 13 billion years old. So when we start talking about how do we know how old the universe is, well, we know the universe has to be at least 13 billion years old in order for the stars in these globular clusters to have lived long enough to start to evolve off of the main sequence. So typically globular clusters are going to be very old, made of very not very, but lower mass stars that are more red, and then open clusters are usually going to be younger, more bluer stars. So we have these two types of clusters, the open clusters and the globular clusters. And then using the HR diagram and where the main sequence turnoff is, we can use the HR diagram to figure out how old the cluster is. And that's all a function of knowing the kind of the lifetimes of these stars, and if we don't see stars that are around that have those higher masses, we can assume that they've all already gone through their life cycles and have died.